morning and welcome to the part 2 of the lecture 1 of unit 1 of organic chemistry 4 course. In this part, I will explain some important reactions of nitroalkanes. Okay, so let us start with the first reaction, which is the ability of nitroalkanes to form salt with NaOH. Nitroalkanes having alpha hydrogens, that means primary and secondary nitroalkanes, can form salt with NaOH to dissolve in NaOH, which means that nitroalkanes are acidic in nature. They are acidic in nature. Normally, an acid reacts with a base to form a salt. If nitroalkanes are forming salt with NaOH, that means nitroalkanes are acidic. What is the property of an acidic compound? Generally, an acid can easily donate its H plus ions. That is the important property of an acid. So, a compound, an acid can release H plus easily. That means the remaining anion, in this case carbanion, if it is stabilized, then that means that compound can easily donate H plus. So here nitroalkanes having alpha hydrogens are acidic in nature because the anion so produced, the carbanion after releasing its H plus is highly stabilized by extended conjugation as shown below. This is an example for primary nitroalkane. This primary nitroalkane is having two alpha hydrogen atoms. One is this one and second is this one. On treating with OH minus, it takes an H plus from here to have this carbanion. And if you see clearly, this carbanion is resonance stabilized by these three canonical forms. So this carbanion is highly stabilized, means there is a tendency to form this carbanion by releasing this H plus, by giving away this H plus. So if we treat this nitroalkane with OH minus, it can easily give away this H plus ion to form this stable carbanion. That is why nitroalkanes having alpha hydrogens are acidic. That is why it can form salt with NaOH. But tertiary nitroalkanes having no alpha hydrogen atoms will not form any salt with NaOH because there is no H plus to be given away. Okay. Now we move to Henry reaction. Henry reaction is a base catalyzed carbon-carbon bond forming reaction between nitroalkanes and aldehydes or ketones. See, this is nitroalkane. Definitely it should contain an alpha hydrogen atom. That is mandatory requirement. It will react with a carbonyl compound in presence of a base. A new carbon-carbon bond from this one to this one. A new carbon-carbon bond is formed. This reaction is known as Henry reaction. The mechanism is very simple. We know from the last slide that a nitroalkane containing an alpha hydrogen atom is acidic. It will react with OH minus to form a carbanion, that is this H is given away as H plus to the base. And we know the resonance stabilization, the three canonical structures of this carbanion. I am not showing it here. This carbanion is, we know that it is nucleophilic. It will attack this carbonyl carbon and this C double bond O, this double bond is shifted to O, these bond electrons are shifted to O so that it becomes O minus. And that O minus takes H plus in the next step to form OH. So a new carbon-carbon bond is formed between this carbon and this carbon. This reaction is known as Henry reaction. Primary and secondary nitroalkanes give Henry reaction. Tertiary nitroalkane will not give Henry reaction because there is no alpha hydrogen atom in tertiary nitroalkane. Now we move to another important reaction. It is called as Neff reaction. It is nothing but the conversion of a primary or secondary nitroalkane. That means a nitroalkane containing at least one alpha hydrogen atom to the corresponding carbonyl compound. See the example here. This is a secondary nitroalkane. First on treatment with base, then followed by treatment with acid. You get a carbonyl compound. Nitro compound is converted to the corresponding carbonyl compound. This reaction is known as Neff reaction. The mechanism is very simple. You can see it here. So you know that from the previous slides, nitroalkane having an alpha hydrogen atom is acidic. It can donate its alpha hydrogen atom very easily to leave a carbanion because this carbanion is highly stabilized by resonance. See, this base can take this H plus easily to give this carbanion. And this carbanion is converted to this form by shifting this electron to here, by donating this electron here to form a double bond here. If a double bond is formed here, this double bond will not stay here. This bond will be shifted to oxygen. So oxygen becomes O negative. So in first step, this H plus will protonate here to become an OH here. Again, this O minus will take H plus to form another OH here. Now you see this carbon is highly electrophilic because of the presence of an N plus positively charged nitrogen here, an electron withdrawing group. So a nucleophile such as water can easily attack here. So see here, oxygen of water having a lone pair here will attack here because it's nucleophilic. It will attack here. So a new bond is formed between this oxygen and this carbon. When a new bond comes here, this double bond will not stay here. These bond electrons will be shifted to N plus so that the positive charge is neutralized. There is no positive charge here. So when the lone pair of electrons of oxygen is donated for a bond formation, oxygen becomes positive charge. In order to remove this positive charge, one of the hydrogen leaves as H plus. So H plus goes so that it becomes OH. And this OH is protonated. H plus comes here on lone pair of, there is a lone pair of electron here. So H plus attacks here or H plus comes here so that it becomes O plus H2. In the next step, you can see that there is another OH. This OH bond electrons are shifted to here to become to form a double bond here. So single bond becomes double bond here. So when it becomes a double bond, this bond will not stay here. So the bond electrons will be shifted to here so that O plus get neutralized. It leaves us water, H2O. So it's a easy leaving group now. So when this bond comes here, this bond leaves, so it leaves us water. So we get N double bond O. H plus goes, so N double bond O. See, N double bond O. And in order to get a ketone, these bond OH bond electrons, these electrons are shifted to here so that H plus is released from here. So this bond is shifted to here, that means H plus is released. This bond becomes a double bond. If this is becoming a double bond, this bond will not stay here, it will be shifted to here so that it becomes N, it leaves us NO minus. NO minus will take the H plus which is released from here to form HNO, and this portion becomes the carbonyl molecule. So this is the mechanism of Neff reaction. See here, from this portion carbonyl is formed. This bond is shifted to here, C double bond O, C double bond O, R1, R2, R1, R2, a carbonyl bond, a carbonyl compound, and HNO is formed. This reaction is known as Neff reaction. The next reaction is reaction with HNO2, which is a very important reaction because this reaction can be used to distinguish between primary, secondary, and tertiary nitroalkanes. The reaction is like that. Primary nitroalkanes react with the nitrous acid HNO2 to give a blue solution, which then dissolve in sodium hydroxide to give a red solution. If it is a secondary nitroalkane, then it reacts with nitrous acid to give a blue solution, but it will not dissolve in NaOH to form a red solution. A tertiary nitroalkane will not react with the nitrous acid, so it will not give a blue color with HNO2. This is how we can distinguish between primary and secondary and tertiary nitroalkane. And let us see what is happening there. See, this is primary nitroalkane. On treatment with HNO2, nitrous acid, we know that alpha hydrogen atom can be easily replaced, can be easily given away. So this H is replaced by NO. You see, NO. So now this is nitroform. You see, this is a nitroform. This nitroform can be tautomerized to the more acidic aciform. This bond is shifted to here, so the double bond will come here. So this will not stay here. This is shifted to oxygen. So O minus will take H, OH, which is more acidic. And this acidic aciform will take NaOH. This is the reason for the blue solution. And that blue solution of aciform of this compound will react with NaOH. So we take this H plus to form H2O, OH and H will react to form H2O and Na comes here, ONA. So red solution of the salt is formed. This is why a red solution is formed. Again, NO replaces H to form this nitroso compound. This nitroso compound will be converted to its aciform, that is this H bond comes here, double bond becomes here, so the double bond is shifted to here, so O minus will take H. So this is the aciform. Aciform is acidic, so it will react with NaOH to form this red colored salt. In some textbook we will see, we can see like this also. That means this form is converted to nitroic acid form. That is nothing but tautomer of this form. This bond is shifted to here, so double bond comes here and N double bond O becomes O minus, and O minus will take this H. In other words, for simplicity, I can say like this. There are two hydrogens here. Okay, those two hydrogens and oxygen will combine and eliminate as water. So it becomes N, this oxygen and these two hydrogens will go. So N, C double bond NOH, C double bond NOH. This is nitroic acid, and nitroic acid will react with NaOH to form its salt, which is red in color. So we will focus in this way. Nitrosoform, it is converted to its aciform, which is more acidic, and this acidic aciform will react with NaOH to form a sodium salt, which is red in color. Let us see what will happen in secondary nitroalkane. Secondary nitroalkane react with HNO2 to give blue solution of nitroso nitroalkane. and it will not dissolve in NaOH due to the absence of further alpha hydrogen atom. Let us see. So this is secondary nitroalkane. There is one alpha hydrogen atom. So it is replaced by NO. So it is nitroso-nitroalkane. So this nitroso-nitroalkane will not be converted to its acid form because there is no other hydrogen atom here. If there is another hydrogen atom here, it can be converted to that hydrogen bond will come shifted to here to become a C double bond N, so that it will go as O minus and O minus will take H plus. So such kind of a hydrogen atom is not here. Further high alpha hydrogen atoms are not here, so it will stay here. Blue solution is formed. It will not be converted to a salt, or it will not be converted to a red color solution. So secondary nitroalkanes react with HNO2 to form a blue solution of nitroso-nitroalkane, which will not be converted to its acid form, or it will not be converted to a salt with NaOH because there is no further acidic hydrogen atom. And for this commonly is called as pseudo-nitrol also. It is also known as pseudo-nitrol. And see what happens in tertiary nitroalkane. Tertiary nitroalkane does not react with nitrous acid. There is no alpha hydrogen atom, so it will not react with HNO2. So it will not give a blue colored solution. So this is how primary, secondary, tertiary nitroalkanes can be distinguished. Primary nitroalkanes will give a blue colored solution with HNO2, which on treatment with NaOH is dissolved in NaOH to form a red colored solution. But secondary nitroalkane react with HNO2 to form a blue colored solution, but it will not dissolve in NaOH to form a red colored solution. Tertiary nitroalkane does not react with HNO2 to give a blue colored solution. Thank you very much for your kind listening, and I will see you in the lecture 2 of this unit 1. Thank you.